So hello guys, welcome to the today's LeetCode problem of the day. So today's LeetCode problem of the day is basically the minimum cost walk in a weighted graph. So this is the weight manipulation kind of the problem plus the graph problem. Okay, before getting into the problem, let's understand what is the problem is given to us. So the problem is given that there is an undirected weighted graph. So graph is undirected, so that if there is a edge between u to v, so edge will be v to u as well, with a n vertices labeled from 0 to n minus 1. You are given an integer n and array edges where edges of I is a u, v, w. U is a start node, v is a end node, w is a weight of that edge basically. Okay, and the walk on a graph is a sequence of vertices and edges. The walk starts and ends with a vertex. Okay, and each edge connects the vertex that comes before it and the vertex that comes after it. It is important to note that the walk may you visit the same edge or vertex more than once. So for example, if my graph is given me some kind of like this, okay, so what may happen, I can go from here to here, I can go from here to here, and again I can go from here to here. So that is also the part of the walk only. Okay, this is what they have given to us as a input of the problem. Make sense? So now the cost of a walk starting from the node u and ending at a node v is defined as the bitwise and of the weights of the edges traversed during the walk. Okay, we have to keep this in mind. In other words, if the sequence of edge weights are encountered during the walk, like w0, w1, w2 and still wk, then the cost is calculated as w0 and w1 and w2 and so on, and denotes the bitwise AND operator. Okay, you are also given the 2D array query where query of I is a start node and the end node s and t. For each query you need to find a minimum cost of walk starting at vertex si and ending at a vertex ti. If there exists no such walk, then answer is a -1. Okay, and return the array answer where answer of I denotes the minimum cost of walk for every query I. So let's understand first of all what is a walk. Okay, we have already seen walk means travel from one node to the another node, and you can travel the same edge multiple times. That is also the given them. Now other words is that for query of I we have given a s and t. Make sense? We have given the s and t, and we have to find a path from s to t in a graph. For example, this is my input graph. Okay, this is my input graph I have given. This is my s node, this is my t node. You have to find a path from s. Okay, you have to find a path from s to t where the cost of weights, because each edge is associated with some weight. Makes sense? So you have to find a path with minimum cost such that this w and w and w, whatever the w are there, like suppose this is w1, w2, w3, so 1 2 3 should be minimum. Okay, should be minimum as much as possible, and we have to return it for this query where query is representing the s and t. Okay, so one thing before getting into the problem, you should know few rules of the bitwise AND operator. Okay, bitwise AND. What is that rule? Rule is that the bitwise AND operator of any two numbers, okay, the AND operator of any two numbers is always same as number or decreases. You have to keep this in mind. But it never increases. Basically, it never increases. Why I am saying it? For example, my given two numbers are x comma y. If my x value is 10, if my y value is 2, correct? So what is the representation of the binary representation of x? That would be 0 1 0 0, right? 2 raised to, that will be the 1, that will be 4. So no, this should be 1 0 1 0, right? This is a 10 representation. 2 representation is a 0 0 1 0. So bitwise AND of this is 0 1 1 1 0 0, so which is basically the 2 only, correct? So bitwise AND of two numbers is always decreases or remains same. And what is our goal? We have to find the and of the path which is a minimum. So you have to understand that as long as you are going to increase these numbers, your and is going to decrease only, decrease or less than, correct? So if here is x1, x2, x3, x4 you are bringing, this and will be trying to decrease or equal. So that is clear, right? We have to increase the number of edges in our path from source to the destination, so that we can decrease the and operation over here. Why I'm saying is, let's understand this with a test case. So this is a test case given to us as an input, okay, and we have given the path. What is the query of I? That is 0 to 3. So we have to find from 0 to 3 the path. What is the 0 to 3 path? Straightforward, right? This path and this path. So 7 and 7, okay, it will be 7 again, because 1 and 1 is 1. So that's why 7 and 7 and operation will be 7. So this is the straightforward answer. But for this query, answer is 1. How it is coming? It is taking this 7, okay, and this 1 and 7. Now it becomes 1. How? 7 and 7 is 7, so we can neglect this. So 7 and 1, if you take the AND operator, would become a 1 only. Okay. Okay, so 7 and 1 would give you the 1 only. How it is? So let's represent 7 in binary. So 7 in binary would be this much, like 4, 2 and plus 1, that is 6 plus 1, yeah. And 1 would be in binary, 1 would be like this. So 1 and 1, 1, else it will be 0, because anything with 0 is 0. So 1. That's why answer is coming 1. So what is the goal here? So for any query, okay, for any query that is 0 to 3, take all the ands of all the edges present in that component. So this represent the one component, correct? Component 1, and this represent the component 2. So if you want to find the query, if you want to find an answer for any query, if this 0, 3 belongs to this component, then find the and of all the edges. Why I am saying it? Because see, you can go from here to here using any path. You can go from here, you can come again, you can come here, you can come here, and you can go again. So it is possible, right? So you can include all the edges, and you know, right, the answer for the bitwise and is minimum as much as the number of numbers you are adding in the AND operation, basically, right? If you are taking the AND of 2 numbers, it is possible that that can be less than or equal to that numbers. If you are taking 3 numbers, it can be possible that the AND will be the minimum as a for compared to the 2 numbers. So makes sense, right? So as we see here, so if you take a straightforward part, so and is becoming 7. If you take the all, if you can include all this, the answer is becoming 1, which is a minimum, and that is our goal, to find the minimum and of the all possible edges in the path included. Now the second query, okay, for the second query, let me just remove this, yeah. So for second query, where 3 and 4 is given, but you can see the 3 and 4, there is no path, no path. So if there is no path, so of course, if there is no path, if they does not belong to the same component, so answer will be -1 only, correct? Makes sense? Yeah. Now let's go to the second test case. So this is the graph for the second test case, and what is the query? 1 to 2. So if you see from 1 to 2, there is a straightforward path with a 6 as answer. So you can say, yeah, I will put answer equal to 6, but no. What is our goal? Our goal is to find the minimum of all possible paths. So what I will do, all the paths present in this component, I will take it. That is 15 edge and okay 6 and 7 and 1, because it is possible, right? I can include everything. Why I am saying it? See, if I am here, okay, I have to find from 1 to 2. I can go from here to here first, then I can go from here to here, I can go from here to here, and again I can come back from here to here, because it is undirected graph. So I can include all the edges, right? So if you take and of all these things, it will become, let's see, 15 is represented as 1 1 1 1, 6 is represented as 0 1 0 0 1 0, 7 is represented as 1 1 1 0, 1 is represented as 0 0 0 1. So if you see all 3 are 0, so it will become of course 0. You can see 1 and 0 is 0, 0 and 1 0, 0 and 1 0, so 0. So ultimately we are getting as a 0 as an answer, and you can see the output is also 0. So what is our goal? Our goal is that first of all, find the component for all the nodes in that given graph. So if you see here, the component is only 1, right? Component is only 1, But in the previous case, there were the two components, that is the C1 and C2. And whenever you are checking the query, first check whether the both node belongs to the same node, same component. If both nodes belong to the same component, it means the answer would be the AND of all edges of that component, AND of all edges of that component, correct? Because if you find 0 and 3, for this just take AND of all the edges, that is 7 and 1, it will give the answer. For 3 and 4, check the component is not same, the answer would be the -1 for this. Make sense? Now what are the steps that we have to follow in order to solve these questions? First steps, okay, I will just write here the steps. The steps are simple. First, find component of all nodes. Make sense? You have to find the component of all nodes, and you can find this using the BFS or DFS, or you can use the disjoint set over here, or union find. Anything you can use to find it. You just have to check whether two nodes are belonging to the same component or same parent, basically, are the child of the same parent. Second, once you find the component, iterate, not iterate, I would say find bitwise AND of all edges of each component. This is the second step, right? Makes sense? We have to find the bitwise AND of the all edges of the same component, of each component, basically. And third step will be, okay, iterate over the queries, because we are building the answer. Iterate queries, and there will be the two conditions. First check whether U and V belongs to same component, because this is something that, correct? So if yes, if no, first of all, then put it as a -1. If yes, then answer of I, okay, whatever we are at for that query of I would be the component, whatever the component is having, components and, okay, components and whatever the AND operation we have calculated, and this is how you can solve this problem within the 3 steps only. So I hope you got the intuition for this problem. Let's understand this with the help of the code now. So this was the function given to us, right? And what I have also written the steps here to better understand. So what is the steps? Basically, if you see, the steps are that find the components for each node, correct? So if component is not same for 2 nodes, that is the answer is -1, because if they does not belong to the same component, you can't travel from one node to the another node for them. For all the components, find AND of all edges, that also we discussed, because the AND decreases as the number of element in AND operation increases. This is the property of the bitwise AND, and opposite to the OR. The OR increases as the number of elements in a OR operation increases, correct? Now what I have done, okay, what is given to us here as an input? What is the given to us? Basically, we have given the edges over here, we have given the query. What I did, I created the components array, because the component of any index, for example this index, represent me for each node, okay, n is given number of nodes, so the nth index in a component shows me what is the component for that node, okay. That's why I have taken it as the same length. Visited I have taken because I am going to build first the component array. This component array I am build using the DFS. Component number initially 0, I will be taking, because if there are 2 components, right, I will be doing DFS for all the n's. So once I am done with this, I will increase my component number by 1 plus 1. So this will ultimately belong to the component number 2, and this will belong to the component number 1, correct? I have built the adjacency list, correct? I have just taken that like this. Okay, I have kept it like this. Okay, let's make a dry run. Okay, that will be the best thing if you make the dry run of the given test case. What is the given test case is here? So yeah, 0. Let's take this one, 0 1 3 2 4. I will just take that one only. 0 1 3 2, ages are given and 4 is given here, correct. Now my adjacency, okay, my adjacency would be looking like this. I can, from 0 I can go from to 1, from 1 I can go to 0 to 3, for 2 I can go to 1, for 3 I can go to 1, and for 4 I can go to nothing. Makes sense? Now for I and range, okay, I am doing this. If I is not in adjacency, I am just putting adjacency of is empty, because for this condition, because this is not given in ages, so that's why to handle the edge case I have added over here. What I have done, if I have not visited the current node, then component number increased by 1 plus 1, because initially it is I have, you can see I have initialized with 0, so I am just increased by 1. I am just doing DFS, I am traversing. So if I am starting from this node, right, so what I will do, I came to here using DFS. So this will, I will mark this component number as a 1. From here I can go here, the component number would be 1. From here I can go here and here, so component number will be 1 and 1. Done. Now at the next step in this for loop, okay, in this for loop I can see not a visited of I, but already I have visited, so all this will be marked as a visited, correct. So I will not go there again. Now I will come here, I will increase my component number by 1, that will be the 2. So this 4 is belonging to the component number 2. Makes sense? Now I have built the component array. Now I will, what is our next step? Find the bitwise AND operation for all the edges in the same component. You can see I have initialized it with the greatest number in integer series, that is a 2 raised to 31 minus 1. So all elements are 1 1 1 1 1 1 1 1 basically. Okay. Now I am iterating over the edges. Same thing, I am iterating over the edges. What I am doing, I am taking the component number first of all for any of the edge, correct. I am taking the component number and then I am just putting for that component bitwise, and for that component number should be equal to the weight of all. So this is nothing but what I am doing, I am taking the 7, I am taking this 7, I am taking this 1. So 7 and 7 and 1. I am doing this and I am just putting the component bitwise, and for the component number 1 is basically the 7 and 1. Okay, which is ultimately I guess 1 only, correct. So this is what I am building here. Then I have built the answer array over here. What I am doing in answer array, I am just checking first of all, if the component of u and v is not equal, then put a -1, because they does not belong to the same component. Or else what you have to do, just find out the component number for the u and answer dot append whatever the bitwise operation we have find for this component, just put it and return it. I hope you understand this. Time complexity would be the big O of n plus e. Okay, n plus e. Why I am saying this n plus e? Because see, this operation is going to take the big O of q only, number of queries, and this operation would be taking the big O of n, or big O of component, whatever the number of component, that is the big O of n only, correct. Then the DFS would take the big O of n plus e, because for each edge, okay, and we are traversing for each node, we are traversing the all the edges, so big O of n plus e would be there. So worst case, and the space would be the big O of n, because we are using the adjacency list of representing the all nodes. So I hope you understand this problem. See you in the next video. Thank you.